Howdy and welcome back. Today's lesson is going to be on raw pointers are difficult to love, and we're going to highlight some of the reasons that Scott Myers provides in his textbook, Effective Modern C++. So let's go ahead and get into it. So first and foremost, I'm sure within our own applications, we're hopefully using a good naming convention, and we're aware of which pointers are pointing to single kind of dynamically allocated objects versus pointers that are pointing to a collection of dynamically allocated objects. If we were to use a non-descriptive name, it kind of becomes ambiguous as to whether or not a particular pointer is pointing to, say, a single object, such as this. Let's go ahead and say int p is equal to new int. Let's go ahead and initialize that dynamically allocated object with 7. Notice here that p is going to be an object in its own right. It is a pointer to some sort of integer object allocated on the free store that's initialized with 7. Notice that we could also do something like int p is a pointer to an integer object, which is actually going to be a block of contiguously allocated integer objects. And let's just go with 2 to keep my diagram a little bit easy and to the point. In this case, p is the base address. So p is a pointer, but it's a pointer to the base address of an array of 2 elements. And since we did not specify what those elements are initialized with, they take on whatever's kind of left over in the region of memory that the free store manager allocated to us. But just looking at these names, it's not clear that P is just, if we just saw it presenting or floating around within our programs, well, is P pointing to a single object or a collection of objects? It's not clear. Their declaration doesn't necessarily indicate this to us. Raw pointers are difficult to love for maybe another reason too. Their declaration reveals nothing about whether you should destroy what it points to when you're done using it. Think about this for a second. What do I mean by this? Well, maybe you took the hint from this arrowed bullet point here. The question becomes, what pointer actually owns the thing being pointed to? And in our application, we could have, say, some dynamically allocated object storing 7. And then within our program, there might be multiple pointers to that single object. And the question becomes, when do we deallocate the memory associated with this dynamically allocated object? Is it once the last kind of pointer goes out of scope? But if so, how do we know that the last thing that was pointing to this dynamically allocated object has gone out of its scope and should free its memory? Moreover, maybe a number of different pointers kind of point to this object throughout the lifetime of the dynamically allocated object 7, but maybe one only actually owns it, and 7 should only be destructed once that object goes out of scope. And in that case, even if other things are still pointing to it, maybe we allow them to be, say, dangling pointers in that case, because the object that owned the resource was destructed. So these are just things to think about. But yeah, the kind of question that comes down to it is, which pointer actually owns the thing being pointed to? Because it will be that object which should be responsible for the deallocation of the dynamically allocated object. Now, kind of getting into this a little bit more, we haven't necessarily seen this application in this class. We've let the destructor handle everything, but that's not always the case. So another reason why raw pointers might be difficult to love is because if you determine that you should destroy the thing that the pointer is pointing to, so like in this case, maybe we find out that, hey, when this pointer's lifetime is up, well, the dynamically allocated object that it owns should be deallocated for 2. What this point is communicating is that, well, we might not be sure how to perform that deallocation. So should you use the delete command, or is there a different destruction mechanism that should be associated with the teardown of the dynamically allocated object? Maybe there's a dedicated destruction function that the pointer should be passed to. When we get into more elaborate and sophisticated C++ programs, this becomes a bit more complicated of a problem than one we've seen of the more, I guess, kind of more trivial cases to date. But the good news is I don't believe we'll have to worry about this particular instance within the scope of 128. I don't have anything planned to get into this in more detail or talk about allocators, deallocators, etc., especially not getting into custom definitions of the new operator nor the delete operator for user-defined types. But those are operators, and we can totally define different processes involved with them. And then there's some additional considerations that can go into the construction of objects of user-defined type in place using allocators, and then their destruction, of course. So let's say you figure out how to delete the object. At this point, it might not be possible to know whether to use the single object form or the array form. So let's just assume that, the delete operator is the way to go. Well, how do we know if, we just have a pointer, right? It has an address to some sort of dynamically allocated object. If I didn't tell you how it was constructed, how would you know how to go about the destruction process when you're done with it? And hopefully, you'd understand based off of if you're requesting some sort of contiguous allocation block of memory from a function, it gives a address back to that location of memory that you requested. Well, at that point, you're kind of the owner, so you should be responsible to perform the deallocation. The question is, how do you ensure that in all kinds of sorts of various instances that you are using the correct form of delete? Because if you are using the incorrect form, well, the results are going to be undefined. So let's assume that you ascertain that the pointer owns what's being pointed to, and you discover how to destroy it. It's difficult to ensure that you perform the destruction exactly once along every path in your code. And this is getting back to this idea of ownership that I kind of expressed here. The problem is that, okay, let's say I deallocate this object here highlighted in yellow. How can I know that the pointer storing the address to the now allocated object know that they're actually dangling pointers at this case? So let me get back to where we were. So missing a path leads to resource leaks. So maybe we allocated something, we forget to deallocate. Well, that's problematic, but also problematic is doing the destruction process more than once leads to undefined behavior. And when we introduce dynamic memory, we showed that invoking delete twice on the same address. So once we've returned the thing, that's when we introduce this concept that we're unable to return the same thing twice. And if we do, we saw that runtime error pop up in our program execution terminate. So, I mean, there's all sorts of kind of considerations here. It's like, so if we have multiple pointers, which one actually owns the thing? Okay, if I'm done with it, how do I actually perform the deallocation for the dynamically allocated object being pointed to? Is it delete? Is it some function that I was intended to pass the address to? If it is delete, is it the singular form or the form used to be invoked on arrays? Finally, okay. Now we have all those, even if we know what owned it, we had the case where potentially other pointers were pointing to that object. And then, how do we ensure that we're not inadvertently calling delete twice? How do we kind of consider or know that those pointers are dangling? There's a whole kind of bunch of things that go into the process of memory management when it comes to C++. And as the applications get bigger and as kind of maybe the lines or boundaries of ownership become skewed, this becomes more and more of an involved process that you have to be very considerate in what you're doing. And this is, just moving in. So there's typically no way to tell if the pointer's dangling. It's not like, so remember, the pointer stores an address. There's those pointer operations like dereference. There's something called pointer arithmetic. But nowhere have we discussed and nowhere is afforded by the raw pointer type the ability to go, hey, are you a dangling pointer? And again, remember that dangling pointers arise when objects are destroyed while pointers are still pointing to them. For instance, maybe we have this relationship. So this is a pointer pointing to, let's just go with that integer object. This is another pointer. Let's say we go ahead and perform deallocation. So let's say we delete that address or call delete on that address and then set this to null pointer. In this case, recall that this pointer here is still dangling, right? Because it still stores the address to the object whose memory was just deallocated for. And there's no easy way to catch this using raw pointers. So again, it becomes this kind of choreography of ensuring that when we are returning things, we're kind of informing or somehow conscientious of the fact that other things may still be pointing to them. So how do we ensure that, or how do we deal with this dangling pointer problem? And I'll go ahead and just conclude this section with a quote by Scott Myers, taking directly from his Effective Modern C++ textbook. He says, raw pointers are powerful tools, to be sure, but decades of experience has demonstrated that with only the slightest lapse in concentration or discipline, these tools can turn on their ostensible master. So this is a very complicated process of dealing with dynamically allocated objects, dynamic memory management, and even those who have years and years of experience, this is still a non-trivial task, especially when the applications become more and more involved. So now we're going to move on to how we can use smart pointers to perhaps accommodate or allow us to address some of these, I guess we could call them perceived issues of raw pointers in a way that will make our life um, a lot easier. It'll diminish kind of the cognitive overload associated with using dynamically allocated objects. And we'll see that the implementations for these are really cool. It's some really neat design, and I'm excited to share that with you. So let's go ahead and finish this video before I ramble too much and move on to the next.